Welcome back. I'm Ulysses, your host for this Ask Our Expert series about clocks and timing. In today's video, Sieg explores frequency stability, how to quantify, and provide some examples to illustrate the concept. So Sieg, what is clock stability?
When I talk about stability now, the overall goal here is so that we can have a quantitative way to describe what stable means instead of using qualitative terms such as stable, very stable, not too stable, something like that. So, frequency, you may recall, consists of two components. It consists of the repeating event, and it consists of a time interval between when these repeating events occur or these repeating clock edges occur. Let's take the example of a train that's scheduled to leave at 8 o'clock in the morning every day of the week, every day of the year. The event is the train departing the station, and the time interval between the event occurring again, between the train leaving the station again, is 1 day or 24 hours. But does this train leave at exactly 8 o'clock a.m. every day all the time? What if, for example, the train on one day leaves at 8:01 a.m.? The time interval is now 1 day and 1 minute. It's 1 minute longer than it's supposed to be. And so the time interval has an error, a time interval error, sometimes abbreviated as TIE, of 1 minute. Or let's say on another day, the train leaves at 7:58 a.m. The train has a time interval error of negative 2 minutes because the train is leaving 2 minutes before it's scheduled to leave. If we observe a repeating event over a long period of time, we can measure and quantify the stability instead of using qualitative terms. Now, the requirements we have to do this are simple. We need to have many time intervals. So in other words, many events happening over a long period of time. And for each of those time intervals, we need to record the time interval error. Now, after we take those many samples of data and we record the time interval error for each of those time intervals, we choose the maximum. So we get a time interval error maximum for a given period of time. And that's the way we describe stability. So let's put this into a real example to make it a little clearer. Let's go back to our 8 a.m. train. Let's say that we measure this 8 a.m. train's departure over the period of 10 years. So there's many events, many time intervals, so that requirement is met. And let's say that when we measure the time interval error over that period of 10 years, it is the maximum of 20 minutes. Another way of saying that is that the train is always leaving at 8 a.m. plus or minus 20 minutes. Let's say we have train number 2 that we also make these same measurements over a 10-year period, and we discover that train number 2 is always leaving somewhere between 7 a.m. and 9 a.m. So now the maximum time interval error is 1 hour. This train, which has a higher maximum time interval error for the same 10-year period, is less stable. Or let's say we have a train that over this 10-year period is just great. It leaves every day between 7:59 a.m. and 8:01 a.m. So we're talking 8 a.m. plus or minus 1 minute. It has a maximum time interval error of 1 minute over a 10-year period. And of course, this train has a more stable departure time. Its event is more stable than the other two train departure time events that we just talked about. Now, clock sources are described the same way with their stability parameter in their data sheets. So for example, you may have a crystal oscillator that says in its data sheet that it will remain within plus or minus 50 ppm, 50 parts per million over a 10-year period, or perhaps plus or minus 25 parts per million over a 10-year period. That is what we see on the data sheet expressing that oscillator stability.
Sieg, thanks for that explanation on how frequency stability works. To our viewers, make sure to click on the links below for documentation on frequency stability. And as always, don't forget to subscribe to our YouTube channel to be the first to know when we have more insights from our experts. We'll see you next time.